Today I wanted to start with going over this function. This is a quadratic function, and we're going to go through what that means here in a second. But the quadratic function here is f of x equals 6x squared plus 12x minus 1. And there's a little bit of a typo here. I got this problem from a student, and I think this was actually from their homework. So the professor or book misspoke here. It says rewrite the quadratic function below in standard form, also known as vertex form. Vertex form is a different form from standard. So these are very different. And if this function was in vertex form from the start, then we should get the vertex right away. But this is actually in standard form. And since it's in standard form and it's not the same thing as vertex form, we can't get the vertex right away. So what I would like to do is go through a few basic components here before we get into actually solving this problem. So what is a vertex? So the vertex of an equation, in this case, of a quadratic equation, is the highest or lowest point of the parabola. Okay. The highest or lowest point on the graph, generally speaking, is what a vertex is. But in our case here for a quadratic, talking about parabola. So what is a quadratic equation? A quadratic equation is one in which the degree is 2, right? So the exponent of the power of the leading term, that is the leading variable in that leading term. So a constant would not have a degree. And that's where we're going to start. We're going to say degree 0, right? Because there is no variable with a constant by itself, right? Yeah. We start to call a constant a coefficient when we pair it with a variable. And in such a case, say we have something like y equals, say, 2x plus 3. This is going to be a linear function, and it is going to have a degree of 1 because x here is assumed to be to the first power if there is no power there listed, right? If we have a quadratic equation like f of x equals 2x squared plus 3 minus 5, this is quadratic, and it is going to have a degree of 2 because the leading term here, 2x squared, the x squared is going to be, the x here, that is going to be to the second power. So it is going to have a degree of 2. Now, quadratic still sounds weird. It sounds like quad 4. But if you imagine a quad, imagine kind of a square in this case. And when we find the area of a square, the area of a square is going to be equal to, say we have a times a here, this would be a times a, which is a squared, which is the same degree as our x variable here. Okay. So when you think of quad, think quad in this way. It is going to be a cubic function, right? Something x to the third power. This is the leading coefficient. A degree 4 would be a quartic function, right? Then it goes quintic and sextic or heptic, or sorry, sextic or hectic or septic or heptic for 7. But it just keeps going on and on, right? So quartic is really what we see for 4. Quadratic, quad, we're thinking 2, right? In our case here. So just think of that. That's why we say it is a quadratic. Now, as we go through here, we want to think a little bit about what is a perfect square, right? Because part of the procedure in order to solve this original problem, that we have to complete a perfect square. And first, what we have to do here is we have to factor. And then what we do is we complete the square. And we're really completing the perfect square. And then third, what we're going to be doing, I'm going to say here is we're going to complete the square, separate these, complete the square, and then we're going to rewrite as a perfect square. And then finally, we will expand and simplify and get our vertex form, which will have our vertex in it. So let's talk a little bit about what a perfect square is. So when we first started out, perfect squares, all that meant was we're going to take any whole number from 1 to infinity, really. Usually you memorize these 1 to 15. And you are going to just take the square or raise it to the second power, right? So 1 squared is just 1. It's 1 times 1. 2 squared is 4. It's 2 times 2. 3 squared is 9. That's 3 times 3. 4 squared is 16. That's 4 times 4, and so on and so forth. Now, when we're talking about perfect squares as relates to factoring and equations, right? What we have to do is think of it a little bit differently, because a perfect square in an equation, it's going to be something like x plus 2 squared, right? Which is really, if we break it down, going to be x plus 2 times x plus. So instead of just squaring a number, a whole number, we are squaring an entire mathematical expression that falls within these parentheses. What do we do when we complete the square? Completing the square. So if we had something like a basic quadratic, f of x equals x squared plus 4x plus 5, in order to complete this square, what I'm going to do is I'm going to focus on the coefficient of the x to the first power term, right? This middle term. What I'm going to do is I'm going to take the coefficient 4 and I'm going to divide it by 2. No matter what you do, you're going to divide whatever number when you're doing this, that coefficient, you're going to divide that coefficient of that x to the first power term. You're going to take that coefficient, in our case it's 4, and you're always going to divide it by 2. Okay? And you're going to take that value and you're going to square it. So then this becomes 4. So then what do? You continue to complete the square, which is f of x now times x squared plus 4x plus whatever term we found or whatever constant we found here, 4 plus 5. And then you're going to subtract 4. We can't just add 4 because that would change the entire value of this function, right? This would be then plus 9, right? And it would be a completely different function. But by adding 4 and then also subtracting 4, we are going to negate that chain. So this is a little bit of a trick. This is this is algebraic gymnastics, basically. And then what we do when we're completing the square is we factor this perfect square. So this is a perfect square. And what a perfect square is exactly, we talked just for a moment about what it looks like here, the presentation. But what it actually is that first term and that second term, it is that first term and the last term, the constant. So the first term and the last term, we set them up in such a way so that we can have an expression, right? A perfect square is an expression that can be written as the square of a binomial, the square of said binomial, right? Anything over 2 would be classified as a polynomial. But here, we want to be able to take this and write this as a perfect square, which is, again, the expression that can be written as the square of a binomial. So we want to take 2 things here. We're going to say x plus something times x plus something. And these second numbers here would be the same. So then we can square that function because then it would be the exact same thing times the exact same thing, okay? Which would give us that perfect square. So here, this ends up being x plus 2 times x plus 2, which is just x plus 2 to the second power, aka x plus 2 squared, aka perfect square, right? And we can't forget this last part here, the 5 minus 4 plus 1. And this is our vertex. Now, what is vertex form? Let's take a look. The standard form of a quadratic equation is equal to f of x equals ax squared plus bx plus c. So a is the coefficient of x squared, b is the coefficient of x, and c is no coefficient. So c is a constant, right? In this case, a, the coefficient of x squared actually determines the direction. If it's positive, it's going up. If it's negative, it's going down. It determines the direction of the parabola, and it also determines the width of the parabola. B, it affects the position of the vertex and the axis of symmetry. And then C represents the y-intercept. The y-intercept, as we've discussed before, is going to be equal to, in this case, 0c, right? It could be 0b, as in the y equals mx plus b slope intercept form, but in our quadratic standard form, it is 0c. Is going to be equal to x is equal to negative b over 2a. So we take the coefficient of x, b, and we divide it by 2 times a being the coefficient of x squared. Okay? And then we take the opposite sign of that. And that is going to be the axis of symmetry. Now, a little more complicated is going to be finding the vertex from the standard form. And if this is too complex or this just looks really weird, don't say about it. We're going to find the vertex form, but you can find the vertex straight from the standard form. And it's going to be equal to negative b over 2a, and then the value of the function of negative b over 2a. And if you look at this closely, this is really like an xy pair that we will find as the vertex. But in the standard form, it's not exactly written how we would like it to be. So it's a little more truncated and complicated than it looks. But if I find the value for negative b over 2a, the axis of symmetry, then I can plug that into the function and get out my value, which would be the y. Now, the vertex form is going to be equal to f of x equals a times x minus 8 squared plus k. Now, in this, h is actually going to be equal to the x coordinate of the vertex, and the k is equal to the y coordinate. Much easier in this form. And then a is going to, again, determine the shape and direction of the parabola. Positive a, if I have a positive a value, the parabola will go up. If I have a negative a value, the parabola will go down, right? And the width is multiplicative. So the cool thing, again, about this form is that we have h, which is going to be our vertex. The axis of symmetry is going to be equal to x equals h, right? And when we have a greater than 0, that is positive, the parabola opens up. And then when we have a less than 0, that is negative, the parabola opens down, and it is called the maximum. Makes sense, because if I look at it, a is greater than 0, it's going up. This is going to be the minimum point. A is less than 0, that means the parabola is going down, and this is going to then be the maximum. So let's go back to our original problem and take a look. So you can now see that this is very much indicative of the standard form. F of x equals ax squared plus bx plus c, right? A is equal to 6, and then plus c. So c is equal to negative 1. Okay. So this is the standard form. And what I want to do is I'm going to solve this from first principles. And I am going to walk through completing the square portion pretty slowly here. So if I have f of x equals 6x squared plus 12x minus 1, okay? I want to find the vertex and the vertex form. So first thing I do is I want to get this coefficient alone, because if we look back at our vertex form, it has an a on the outside, right? So let's factor out the 6. So I have f of x equals 6 times x squared plus 2x minus 1. Okay, so this is our first step. We're already done with our first step. This is the factoring part. We're just pulling out whatever we need to get that x squared by itself, right? But when I take out that 6, I have to take it out of the 12 as well. So I get 6 times 2 is 12, or that is 12 divided by 6 equals 2. All right. Now, to complete the square, we need to first take that coefficient inside the parentheses, right? We're completing the square here inside the parentheses, not from here. So what do I get? I take this coefficient, 2, and I divide it by 2. So now in our second step, I'm going to take that, I'm going to divide it, 2 by 2. I'm going to square that. I'm going to get 1. You take half the coefficient of x, which is 2, and in this example, and you square it, and you get 1. Okay. So we add and subtract this value inside the parentheses. And this is part of completing the square. So we have f of x equals 6 times, I'm just going to take what we have up here, x squared plus 2x plus 1 minus 1, right? Because that's what we got here as our perfect square number, okay? And our complete square, that is. So when we complete that square, we get the number that we need to add inside our perfect square. And I'll show you what I mean here in a second. And then if we remember from a bit ago, we don't want to forget this minus 1. This is an additional minus 1 outside of the parentheses that we need not forget. Now 3, what we're going to do is we're going to rewrite it as a perfect square. So f of x equals 6 times, I have my perfect square value here. I'm just going to take x plus that perfect square value, 1. So x plus 1, that quantity. If you want to solve this out, distribute it through, do x plus 1 times the quantity x plus 1, and you will get this value here, x squared plus 2x plus 1. Okay. What we're going to do with this minus 1, you'll see in a second, to that perfect square that we were trying to get to in the vertex form. And then we also still have the minus 1, right? Because this value, x squared plus 2x plus 1, that is the perfect square here. But we still have this minus 1, and then we have another minus 1 outside the bracket. So then what we want to do is we want to distribute that 6. This is probably really more expand and simplify. So f of x equals 6 times, we keep this perfect square as is, x plus 1 squared, because this perfect square is exactly what we want in that vertex form. Now, what we're really doing is multiplying that 6 times that negative 1. So what we end up getting as our final answer is f of x equals 6 times x plus 1 squared minus 7. So according to the vertex form, we have f of x equals a times x minus h, the quantity squared, plus k, in which the vertex is going to be h and k. So minus h, right? And up here we have plus 1. So the normal form would be minus. So if this was minus, then this would be a plus 1 here. But since the normal form is opposite of the form that we have up here, we're going to make this a minus 1. And then the minus 7 is explanatory because this is supposed to be plus k, but it's actually a minus k. So this is minus 7. So the vertex for this equation is going to be 6 times the quantity x plus 1 squared minus 7, which is d. All right. And now I'm going to give you a couple of additional problems. So here are the 3 problems.